So the context of my talk, or the analogy to the contents of my talk, is a phenomenon that happens often, very often, in Lie theory, is that some objects that are infinite dimensional in characteristic 0, they became finite dimensional in positive characteristic. Or at least they give rise to finite dimensional objects in positive characteristic. One of these instances of this phenomenon is the so-called Cartan-Lie algebras that were classified by Cartan in the beginning of the 20th century. There are some algebras of derivations of some infinite dimensional algebras. Then they give rise, they play a very important role in the classification of Lie algebras with finite growth. And then you go to characteristic P, these same algebras happen to be of finite dimension. Another instance is with enveloping algebras of Lie algebras. The enveloping algebras, it's a way to, we can say that this is a way to produce Hopf algebras from Lie algebras. And if you go to characteristic P, you have restricted universal enveloping algebras that have, again, finite dimension, and they are not possess any analog, any finite dimensional analog in characteristic 0. So what I would like to do is to explain how to do this at the level of Nichols algebras. And the plan of my talk, so the main objects are Nichols algebras and braided vector spaces. Then I will explain, I will give some words about these fundamental algebraic notions, and I will explain how to deal with Nichols algebras of the compositions, or what are the open questions and why this is difficult. And then I will explain the new results, which are Nichols algebras of blocks and Nichols algebras of blocks plus points. Okay, so what is a braided vector space? A braided vector space is a vector space together with a solution of the Braid equation. So the Braid equation is a linear invertible map from V tensor V to itself, satisfying this equation. This equation is equivalent to another equation that appeared in physics called the Quantum-Yang-Baxter equation, and has a prominent role in the last 50 years in many developments. And as a matter of fact, all the applications of the Quantum-Yang-Baxter equation really go through the notion of braided vector space. How to produce braided vector spaces? For our purposes of this talk, we will look at the so-called category of Jeter-Drinfeld modules over K gamma, and K gamma is a group algebra over a finitely generated abelian group. And what is a Jeter-Drinfeld module over K gamma? Well, this is a module that has two structures. First of all, it is a left gamma module, and second, it's a gamma graded vector space. And these two structures are related by the fact that the grading is of gamma modules. So the action of the group preserves the braiding. This is the compatibility condition. And each time you have such a Jeter-Drinfeld module, you obtain a braided vector space. So you take the Jeter-Drinfeld module and you take an element V, which is homogeneous, and you decree that C of V tensor W is G acting on W tensor V, and you extend this linearly, and it is easy to see that this is solution of the Braid equation. And these solutions are very important. I will explain later in the classification of pointed Hopf algebras and give rise to a very interesting combinatorics. So this is the first important notion, braided vector space. Now, what is a Nichols algebra? A Nichols algebra is a kind of Hopf algebra. So if you know what is a Hopf algebra, there is a generalization of this notion called the braided Hopf algebra, or a Hopf algebra in a tensor category. And we are interested in Hopf algebras in the tensor category of Dieter-Drinfeld modules. So we need the braiding for that. And our interest on these Hopf algebras in the category of Dieter-Drinfeld modules comes from the fact that there is a construction like this. You take B, you take the tensor product with K gamma, you take the smash product and the smash coproduct, and this is a usual Hopf algebra. So this is the first step in order to classify Hopf algebras. So this reduces to this consideration of this. Now, the crucial definition is that for any Dieter-Drinfeld module, in this case over K gamma, there exists a unique up to isomorphism graded Hopf algebra in this category. So it's not a usual Hopf algebra, it has a braided structure, which is graded and satisfies 4 conditions. One, it is connected, which means that you have nothing in degree 0 except the field. Second, the name B of V comes from the fact that B1 of V is isomorphic to V as Dieter-Drinfeld modules. And the 2 crucial conditions is that B of V is generated in degree 1, so by the B1 of V, and the primitive elements of B of V are exactly those elements of degree 1. So this concerns the algebra structure, and this concerns the co-algebra structure. And it's somehow this somehow naive definition turns out to contain a lot of combinatorics behind, which I will try to explain in some slides. Okay, so there is a theorem saying that there is only one Nichols algebra with these properties, and we call them the Nichols algebra of V. Now, there is a remark which I cannot explain in detail, but the remark says that B of V is the image of a map omega that goes from T of V to a copy of T of V with some different structures called TC of V. And this map omega is called the quantum symmetrizer and depends only on C. And this alternative definition of the Nichols algebra in terms of the quantum symmetrizer shows that you only need to care about the braiding. You do not need to care about the action and the coaction, but on the braiding that this action and coaction induce. Good morning. Okay, so we are ready with Nichols algebra, but the 2 people that arrived, they know this definition already, so I go on. So what is the problem? What is the problem we want to solve? We want to classify all Nichols algebras in this category that have finite dimension, or even more general, finite Gelfand-Kirchhoff dimension. Now, this Nichols algebra is, since it is generated in degree 1, is defined as, it turns out that you have a map from T of V to B of V, and therefore it can be presented by T of V divided by some ideal. And there is a third definition of Nichols algebra that says that this ideal is the maximal homogeneous Hopf ideal intersecting trivial K of the direct sum V. And once again, this is a very nice round definition, but to determine explicitly in general this ideal is very difficult. So even in small examples for small classes of braided vector spaces, one needs to work a lot to determine whether this ideal or whether the dimension is finite or whether the Gelfand-Kirchhoff dimension is finite. And one needs a variety of indirect techniques to deal with this Nichols algebra. Okay, so this is the general context. Now I would like to talk about, which is, one important thing is that we cannot compute all Nichols algebras with one technique. We need different techniques to compute, depending on how is the braiding. Some braidings need some techniques, some other braidings need another different techniques. So I would like to explain what happens for a special class of braided vector spaces called decomposable braided vector spaces. So what is a decomposable braided vector space? So a decomposition of a braided vector space W is a family of subspaces, all different from 0 to avoid trivialities, and with n is at least 2, such that W is a direct sum of these Wi's. And the important axiom is that C of W tensor Wj is Wj tensor Wi. In particular, Wi, each Wi, taking I equal to j, is a braided subspace. And the goal is to study Nichols algebras of these decomposable braided vector spaces, assuming that you know the Nichols algebras of each component. And there are some techniques to deal with this. The first is a remark by Grania many years ago in his thesis. He observed that if you take a decomposition like this with only two factors, V1 and V2, if C squared is the identity, then B of V is kind of tensor product of the Nichols algebra of V1 with the Nichols algebra on V2. But this is the only easy case. But it's good to have it in mind. And this kind of condition appears a lot in the theory of tensor categories with other purposes. Okay. So first example of a braided vector space with a decomposition is the so-called braided vector space of diagonal type. What is a braided vector space of diagonal type? It's a braided vector space with a decomposition whose components or factors have all dimension 1. And I call them points. And this means taking one non-zero element from each component that you have a basis xi of V and a matrix Q such that C of xi tensor xj is qij xj tensor xi. And the qij's are all different from 0. So to this Q, I need to attach a diagram, or generalized diagram, labeling each vertex I with qi, the vertex j with qii, qjj, and if this product qij, qji is 1, I have no h, and if this is different from 1, I put an h between I and j, and I decorate with this label with qij tilde. Okay, then there is an obvious notion of connectedness, and for what I will say, I will assume that the diagram is connected. If V is in this category and is semi-simple, so this is an abelian category, if it is a semi-simple, then clearly it should be of diagonal type. And there is a theorem by Heckenberger that says that the classification of the V in this category, where G is finite, G is gamma, when G is finite and the dimension of B of V is finite, this is known in characteristic 0. I don't have much time to explain the classification. My first proposal for this talk was to explain this classification, which is, I think, very important, but I changed the topic. And let me just say that the proof uses a technology called Weil groupoids, which is very important. It's not yet completely understood, many things are still open about Weil groupoids, how we can use them to other problems. And so the Weil groupoids come with some generalized root systems that, again, I don't have time to explain, but I do have time to say that this is a very important notion. Okay, more generally, suppose that you have a decomposition W direct sum of Wi's, and the braiding of Wi tensor Wj is Wj tensor Wi, as I said before, but assume that the Wi's are simple Dirichlet modules over a Hopf algebra. Then we can attach to W, more generally, a Weil-groupoid, even if it is not of diagonal type. This is a paper with Heckenberger and Schneider, and then they wrote another paper themselves. And this is explained there. This is also very combinatorially very useful. And as an application of this existence of the Weil-groupoid, Heckenberger and Vendramin classified the W's in K of G, where G is a finite group, not necessarily abelian, with n bigger than 1, such that the dimension of the Nichols algebra is finite. And here again, we have a small list. The list is small. And this is a phenomenon I would like to stress. When one tries to classify Hopf algebras, when one starts with some new class of Hopf algebras, one always thinks that there will be lots of examples, and it will be impossible to classify because there were too many examples and too many objects. And at the end of the journey, what you see, what you realize, there are not so many examples. So this is somehow surprising. I don't see any reason to have this phenomenon, but so far this is what happens. At least if you impose some growth condition like finite dimension or finite Gelfand-Kiliov dimension. Okay. So because of what I said, the next problem one has to deal with is to look at Nichols algebras of indecomposable but not simple braided vector spaces. This is naturally the next step to look at. And we do this for the free abelian group, zeta. And it turns out that they are classified by can be classified by two. As braided vector spaces, they are classified by epsilon and L, where epsilon is a number, is an element of the field, a scalar, and L is a natural number. So L is a dimension of V of L2. And in the basis, x1, xl, you have a braiding given by this rule. C of xi tensor xj is epsilon x1 tensor xa if j is 1. So here, so 1 is like diagonal, but the rest is not diagonal. So if j is at least 2, then this gives epsilon xj plus xj minus 1 tensor xi. And in characteristic 0, we have proved that these blocks have finite Gelfand-Kiliov dimension if and only if L is equal to 2 and epsilon is plus or minus 1. And I will call V of epsilon 2 an epsilon block. So these braided vector spaces always give infinite Gelfand-Kiliov dimension except these two cases. And the same problem in positive characteristic is open. It's open. Okay, what happens with these two examples? The first example is taking L equal to 2 and epsilon equal to 1. This algebra, the Nichols algebra of this block, turns out to be a very well-known Jordan plane that appeared in many places. The Jordan plane is generated by two elements, x1 and x2, and the relation is the commutator plus 1 over 2 x1 squared. And it is easy to see that the monomials x1 to the a, x2 to the b form a basis, and that this is a domain, and that the Gelfand-Kiliov dimension is 2. So all this is well known. And if you go to characteristic, to positive characteristic, Sibils, Lauda, and Witherspoon, they realized that the Nichols algebra, in this case, has finite dimension because you have the same two X generators, the same relation like this, which is a quadratic relation, but then you have to add x1 to the p and x2 to the p. Therefore, the dimension of this guy is p squared. So it's Gelfand-Kiliov of dimension 0, and the dimension is p squared. And if the characteristic, for this they need characteristic different from 2 because one has this relation. If the characteristic of P is equal to 2, then they also give the presentation, and it's a bit more complicated, and the dimension is not P squared, it's a bit higher. Okay, so we look at that, we found this reference, and we look at the next example. So what happens with V of minus 1, 2? V of minus 1, 2 can be described as follows. Let me introduce x21 as the x21 is this anti-commutator x2, x1 plus x1, x2. Technically, this is the adjoint of the braided adjoint of x2 and x1. And in characteristic 0, we have proved with Angion and Heckenberger that this has the following presentation. Is obviously generated by x1 and x2. x1 squared should be 0. And you have this relation, which is a cubic relation. x2, x21, x21 is here, minus x21, x2, which is here, minus x1, x21 is 0. So it's a cubic relation. And we call this guy a super Jordan plane. And the PBW basis has x1 to the A, x21 to the B, x2 to the C, where A could be 0 or 1, and B and C are arbitrary, non-negative integers. Therefore, since this is the basis, it's immediate that this Gelfand-Kiel of dimension should be 2. And this is not a domain, of course, because x1 is nilpotent here. Okay, so we thought what happens in characteristic bigger than 2. In characteristic 2, you don't have minus 1, you have only 1. So in characteristic 2, what we get is the Jordan plane characteristic 2. And if the characteristic is bigger than 2, then the Nichols algebra in this case is generated by the same elements, the same relations, but you have to add x1 to the P and x2 to the 2 times P. And this is, if you put here P equal to 2, you get the presentation of the Nichols algebra of the Jordan plane in characteristic 2. So the Jordan plane in characteristic 2 behaves like the super Jordan in higher characteristic. Okay, and this is a basis, again a PBW basis, immediate from these relations, and the dimension is 4P squared. Okay, this is about blocks. But we do not know what happens in characteristic P with other blocks. It is still open. Now, what happens when I would like to see now a decomposition. I would like to understand what happens with a decomposition like this. V equal to V1, V2, etc. And each Vi is either an epsilon block, so one of those in the previous slides with epsilon squared equal to 1, or a point. So all these guys have dimension 1 or 2. Those with dimension 2 are epsilon blocks, and those with dimension 1 are points. And we assume that at least one is a block. At least one is a block. And this is by the following reason. There is a conjecture again in our paper. The conjecture says the following. Suppose that V is of diagonal type. Then, if the Gelfand-Kiel of dimension is finite, then automatically V should have a finite root system. I should say generalized, but. And this says that it belongs to the list of Heckenberger, because Heckenberger, in his classification result, gave not only those of finite dimension, but those with finite root systems. And this conjecture is true in the generic case, which means that all Qij's are not roots of unity. It is also true when the dimension is 2. And we also know that if V is of affine Cartan type, then the Gelfand-Kirchhoff dimension is infinite. And we strongly believe that this conjecture is true, and some people in Cordoba is working on this conjecture. I think that dimension 2 was the crucial step. Anyway, I mentioned this conjecture because we proved that when you have at least one block and the braided vector space has a decomposition like I said, then we have obtained the classification of the Nichols algebras of this shape such that the Gelfand-Kirchhoff dimension is finite. And the proof of our result, of our theorem, uses the conjecture. But it does not use the conjecture in the sense that we reduce the points that we can put here, but along the proofs. And it's not in many places, but still this theorem depends on the conjecture. And this list, unfortunately, it will take me a lot of time to explain because we did this by induction, and at the end there is a condition which is difficult to say in few words. But I will give some hints about this list. Okay. One block and one point. Suppose that you have a block V1 with the basis x1, x2. So the braiding has this form. As I explained before, this is the braiding of x1, x2. Then you have another vector space with dimension 1. So you have one block, one point. V2 is the point, basis x3. The label of this is Q22 because it's a point. And what we assume, looking at the Jeter-Drinfeld module structure, is that the braiding is given like this. So there are three scalars, Q12, Q21, and A. And the Q12 appears here when you braid x1 with x3. The Q21 appears here when you braid x3 with x1 and x3 with x2. And then the A appears here. And we need some terminology to deal with this because there's a lot of notation. So I call the product of these two scalars, Q21, Q12, the interaction between the block and the point. And I will say the interaction is weak if this is 1, mild if it is -1, and strong if it is neither 1 or -1. Okay, and then the other, so these three extra elements have the interaction and also have this scalar A. And this scalar A turns out to be very important, and we call it the ghost because it is somehow hidden in the picture. And when the characteristic is 0, we attach to A scalar G, which is really the ghost, which is -2A if epsilon is 1, and A if epsilon is -1. And we say that the ghost is discrete if this scalar is a natural number, starting from 1. For instance, how this works. So the first lemma says that if the interaction is strong, the Gelfand-Kirchhoff dimension is infinite. If the interaction is mild and the epsilon is 1, the Gelfand-Kirchhoff dimension is also infinite. So this kind of lemmas help us to go on and achieve the classification in this case. Let me use some more generalized Dinkin diagrams. So Dinkin diagrams now have points and blocks. The blocks could be with epsilon 1 or with epsilon minus 1. We have an edge between the block and the point. The edge is numbered by G when the interaction is weak, and when G is 0, I put nothing. Same here. And if the interaction is mild, which says that Q12, Q21 is minus 1, we put a different kind of label to recognize that we are working with a different interaction, which is the minus and the ghost. So it's a bit tedious, but we need this to give the classification. So the theorem is the following. Suppose that you have a braided vector space of a block and a point with the braiding as before. Then, here one should write Gelfand-Kirchhoff dimension. The Gelfand-Kirchhoff dimension, because we're in positive characteristic, is 0, is finite, if and only if V is in this table. So we have some families and some discrete elements. For instance, L1G has a block. The G is discrete. The Gelfand-Kirchhoff dimension is G plus 3. Then L minus 1G is the same, but with a minus block. It's very similar. Then with a minus 1, we have a block G, and here a minus 1. That's Gelfand-Kirchhoff dimension 2. Similar here. And this is an exception, which is the only case where the point has a label which is neither 1 nor minus 1. And in this case, the Gelfand-Kirchhoff dimension is 2. This is a very interesting example. And another interesting example, which also is out of the families, is C1. So this is Cyclop 1, which has Gelfand-Kirchhoff dimension 2 and has a minus block, a point labeled with a minus 1, has a mild interaction. This is what this minus 1 says, and the ghost is 1. And any other example has infinite Gelfand-Kirchhoff dimension. And this is in characteristic 0. Now, we can try to do the same in positive characteristic, and at least 3, so bigger than 2. Same kind of braiding. Now we say that the ghost is discrete if this A belongs to FP star. And in this case, the ghost is a normalized version of A, so I omit the definition. It's a very precise definition. I need to take a representative in zeta of 2A, and I take this representative in this way. And from this representative, I define the ghost by this formula. Okay, this is what means the ghost in positive characteristic. And then we have the following theorem. The theorem says the following. It's a weaker theorem than in positive characteristic. It says, if you have a braided vector space of a block and a point with a braiding as before, suppose that V is on this table, then the dimension of V is finite. And the point here is that we do not have, for blocks, we don't have the reverse implication. We do not know if for a block, which is not V of 1, 2, or V of minus 1, 2, we do not know. It could have finite dimension or not. So we have only one implication here. And the dimensions are very nice, are like this. So these are the 6 families I explained before. So this guy has dimension. There are some conditions on P. For instance, for this one, where you have omega, you should have a root of unity in your field, which a primitive root of unity. So This happens only for some p's, not for all. And the dimension of B of V is 327 times p squared, and so on and so forth. And here appears this algebra K, So the crucial step of the proof of this theorem is to compute this algebra K. So how this algebra K arises? You have the decomposition V1 tensor direct sum V2. In this decomposition, you have a projection from B of V to B of V1 and an inclusion from B of 1 to V2. Then by some theory, by Radford and Majid and some braided version of this theory, you can, from this setting, you can deduce that B of V should be, again, a kind of smash product of K with B of V1, where K are the co-invariants of the projection from B of V to B of V1. And Heckenberger and Schneider proved that this K should be the Nichols algebra, again of a Nichols algebra, of another braided vector space, which is constructed in this way. It's the adjoint of B of V1 on V2. And actually, this identification somehow appeared in a paper by Rosso also, before them. So this says the following: if I know that B of V1 is finite dimensional, then in order to know that B of V is finite dimensional, it is enough to know that the dimension of K is finite. And for Gelf and Kirchhoff dimension, it's the same game. You reduce the study of this algebra to the study of K. And K is another Nichols algebra. And miraculously, this new Nichols algebra turns out to be easier than the one before. It could happen that the Nichols algebra will be more complicated, but it's easier. And so to describe K1, since K1 is generated by this, V2 is generated by X3, so you just need to look at the adjoint of X2 on X3 and the adjoint of X1 on X3, and this generates K1. You compute explicit the braiding, and most of the times this braiding is of symmetric or supersymmetric algebra up to a twist, which means that it's very easy to compute. No? For instance, K here is the symmetric algebra of a vector space of dimension R plus 1. And when you compute this, is the restricted symmetric algebra, it should have this dimension. Okay. So what happens? Let me give more precision on this L of 1G on this first line of the table. So I am looking at this braided vector space. I take this element Zn. In characteristic 0, we have proved that this is generated by X1, X2, and X3. This is the relation of the block. This is the commutation relation of X1 with X3. And then you have to add between the Zn's, which are of this shape, these relations. Z2, ZT, ZT plus 1, Q commutes with ZT plus 1, ZT, and Z1 plus G is equal to 0. So this is a quantum set relation, and this says that these guys quantum commute, Q commute. And from there, it's easy to derive a PBW basis, which is X1, X2, ZG, G minus 1 until Z0, with Z0 is X3, and with any power here. And this is very interesting because this is a domain. This is one of the few domains that we have in the classifications. And the Gelf and Kirchhoff dimension, as I already said, is G plus 3. What happens with this Lestrigon algebra, which will be the subject of the talk by Dirceu, I believe, in characteristic P? Well, in characteristic P, the same algebra has the same shape, except that at the end, well, Since the first part is the block, you need to add x1 to the p, x2 to the p, but then you need to add also the relation zt to the p equal to 0. And from there, you know you have the same basis as before, but you have to cut at these integers, and then you get this dimension g plus 3. Well, what happens in this case? Let me explain this, which is not a domain. Again, a block, again, the interaction, but now you have the difference that now in this point you have a -1. The treatment is similar. You have this relation, which comes from the block. This relation is the Q commutation between x1 and x3, same as before. The same kind of relations, but now, since you have here a -1, this is a super vector space, more or less, and so you have to add this zt to the square equal to 0. And then the Gelfand-Kirchhoff dimension is 2 because these guys are nilpotent of degree 2. And so only contribute to the Gelfand-Kirchhoff dimension these two words, and then this dimension is 2. So this was in our previous paper, and in the characteristic P paper, same situation, you just need to add x1 to the p, x2 to the p to the set of relations. So it's the same relations, except that you add these two. Here the basis is the same, except that now you truncate these two guys, and therefore the dimension of B of V is 2g plus 1 p squared. And the algebra K is the algebra generated by Z1, Z2, Zt. In the case when the Gelfand-Kirchhoff, when you have one block and several points, in characteristic 0, we assume that V is decomposable with V1 a block and V2, etc. points. Then the Gelfand-Kirchhoff dimension is finite in this context if for every connected component of this is of diagonal type, so it has connected components, and either the interaction is 0 or Vj is a sum table. And the Gelfand-Kirchhoff dimension is 2 plus the sum of the Gelfand-Kirchhoff dimension of Kj's. So it's a direct generalization of one block and one point. The message I want to convey is that we just generalize this. And then we have, for one block and several points, we have some very interesting examples like this, which is related to a sub-orthosymplectic algebra 2-4. So I don't want to explain everything. I just want to say that there are two things. The list is shorter than one would expect, and it appears some very interesting exceptions like this. This is also very interesting because it's the only place where you have a ghost which is not 1. Okay. In another setting, when you have a -1 block, the dimension is finite if and only if you have one more example, which is called C2. C2 is this example which generalizes the one I explained before for one block and one point. So again, you see that there are very few examples. And any of these examples deserves to be studied and to understand whether it comes from Lie theory or it's where it comes from. In characteristic P, we have the following result. If we are in the table, then the Nichols algebra has finite dimension. Again, I don't have a converse result, so if the Nichols algebra is finite dimension, I don't know what happens, but at least I know that these are examples. For instance, well, any of these, and these are the dimensions. Again, you need that the order of, for this example, you need that the order, the 3 divides P minus 1. And I am going a little bit fast, so I will give these results, and I would like to take still 5 minutes to explain the classification of Heckenberger that was in my first slide. So, first remark. The Nichols algebra in this characteristic presented above can be realized as Dieter-Drinfeld modules over a finite group. In this way, we obtain concretely new examples of pointed Hopf algebras in characteristic P-2, which are not of diagonal type. Okay, and the second example, the second remark is that there are abelian groups, G, and these, which are Dieter-Drinfeld modules over them, which are decomposable, but they have finite Gelfand-Kilof dimension, but some of the BIs could be neither blocks nor points. So this setting of blocks and points is not enough to describe the classification of all Nichols algebra over abelian groups with finite Gelfand-Kilof dimension. More precisely, the VIs could be semi-simple, but as the braided vector spaces on themselves, but decomposable as Dieter-Drinfeld modules. So the idea here is very easy. You have so this will be homogeneous of degree G. This will be homogeneous of degree H. So if G acts on H non-semi-simple, this will be indecomposable, but if you put the correct hypothesis, but this could be semi-simple by itself. And this situation happens, and we have some partial results towards the classification. We call this situation a pale block. And some of these give rise also to finite-dimensional Hopf algebras or finite-dimensional Nichols algebras in positive characteristics. So this is also one thing that I was in our paper. So let me give you the references, and then let me give you 5 minutes to explain the classification of diagonal type. No? So the references are, this paper is in characteristic 0, and this is in characteristic P, and this is the paper by Sibils, Love, and Witherspoon, and this is the paper by Heckenberger and Schneider. Okay, so give me 5 minutes to explain the classification of Heckenberger, which I believe is very important to have in mind. So to understand what happens, the first example is suppose that you have a braided vector space of diagonal type, so you have a basis and you have a matrix. Then the first example is when this matrix is of Cartan type, or the braided vector space is of Cartan type. And Cartan type means that there exists a generalized Cartan matrix such that Ai equal to Aij, such that Qij, Qji is Qii to the power Aij. And if this happens, there was a first theorem by Heckenberger and previous version by Schneider and myself, saying that in Cartan type, with finite Cartan matrix. So this matrix A should belong to the list of linking diagrams by Cartan and Killing. So this was the first class, but then Heckenberger realized that there is a way to transform the matrix Qij to another matrix Q prime ij, and the set of all these matrices and the set of all these transformations, you can encode them in something called the Weilgrupoid, plus a generalized root system. And another example of this Weilgrupoid is when you have a Lie superalgebra which is contragradient. So there is a classification of simple Lie superalgebras in positive characteristic by Victor Katz, and one of the classes are the contragradient ones, and this is AMN, so the general supergroup, general linear supergroup, and the orthosymplectic, and the examples G3, F4, and D21 alpha. And it turns out that there is a family of Qijs, that are supertype, which means the same Weilgrupoid as Lie superalgebras in the classification of Katz. Contragradient. So there are some Lie superalgebras in the classification which are not contragradient, and they do not give rise to Nichols algebras of diagonal type. But those that the contragradient ones have a one-to-one, not a one-to-one, but there is a correspondence to something called supertype. So this is the second big family. And this family is contained in another family called standard type. So once one understands that you have the Weilgrupoid, then the question is, what happens if the Weilgrupoid is really a Weil group? And when the Weilgrupoid is really a Weil group, you have Cartan type, but there is a slightly larger class, which is standard type, and there are also very few but very nice examples of standard type. But then we realized with Angiono that this phenomenon could also happen in positive characteristic. And even more, there are some exceptional Lie algebras in positive characteristic that have the following feature. They have no Cartan subalgebra. They have several Cartan subalgebras. And when you think on this, it's clear that what happens is that they have a Weilgrupoid. So this gives rise to a class which is called modular or supermodular type, and they can be described as follows. They have, these Nichols algebras have the same Weilgrupoid as some Lie algebras or some Lie superalgebras in positive characteristic. And these are classified. There are some very specific lists. I don't want to explain them now, but they also give rise to many examples of Nichols algebras. In this way, Nichols algebras appear like quantizations in characteristic 0 of these exceptional modular Lie algebras or supermodular or modular Lie superalgebras. And finally, there is a list which the ones that we could not up to now relate to Lie theory, and these are called UFOs. So this UFO n, where n goes to 1 to 12. These are 12 examples that do not fit in the previous scheme. And many times we need to go to prove some result on Nichols algebras. It's difficult to have a proof by just from the definition, so many times we have to go through the lines of the classification, and this is how we go, using this scheme. Thank you very much. Sorry?
Do you have any examples where the Gelfand-Kirchhoff dimension is definitely infinite in positive characteristic?
In positive characteristic, I think so. Many times the Nichols algebra is a tensor algebra. So if you take a diagonal type with, if you take this matrix, and Q is not a root of unity, so then the Nichols algebra is the tensor algebra, even in positive characteristic. You don't truncate.
Okay, so I mean, if you take an upright closure of a finite field, there's no example.
Probably, we do not understand yet what happens in positive characteristic, but probably if you take the braided vector space of diagonal type attached to, which is of Cartan type, and the matrix is affine, probably I can prove that this has infinite Gelfand-Kirchhoff dimension. Because the proof in characteristic 0 is as follows. You don't care about the height, you don't care whether they are truncated or not. You just look at how many roots you have, and since there are many real roots, I think this will have infinite Gelfand-Kirchhoff dimension by the same proof as in characteristic 0.
Something that has infinite dimension, but it comes from something with finite Gelfand-Kirchhoff. I mean, you can start with something in characteristic 0 that has finite Gelfand-Kirchhoff dimension.
Yeah.
Reduce it modulo p, and then you may wind up with something that has finite dimension or not. Is it possible to give an example where the characteristic 0 that has finite Gelfand-Kirchhoff dimension, and the characteristic p version is not finite dimensional?
Well, okay, I just talked about the classification result. So I don't know what happens with an arbitrary braided vector space. In our classification, most of the times we got finite dimensional examples. So the examples that we don't know if the dimension is finite or not is because we didn't have time to analyze the algebra K that appeared there. So in almost all cases, K is easy to compute, but in some cases, K is difficult to compute. And so I could not say that there. So the first answer to your question is I don't know, and the second answer is I am not sure what should happen. My feeling is that always it will have finite dimension, but there are some technicalities that I do not control yet.
And Nicholas, do you think the tables, classification tables that you show in positive characteristic are not complete? Do you believe that there are more?
I don't know. I don't know because until we solve the case of the block, I could not, I don't have an intuition because we need to solve the question of when a block has finite dimension. And even for L equal to 3, so dimension 3 and epsilon equal to 1, we were working a little bit and we didn't finish. And so I have no intuition so far.
But they also selected ones with larger.
No, I don't think so, no.
So you mentioned these exceptional Lie algebras and positive characteristics.
Yes.
Can you say something about them? So what are they Lie algebras? Are they new or?
Oh, these are the algebras we look at on the classifications, like El Duque algebras, Weisfeiler-Katz algebras,
So
this kind of algebras.
I see. So they appeared in literature before.
Definitely. We took from the literature the list of them, and we are, so we don't have, we have a definition which is not completely clear that this definition is good, but in principle what we do is we go case by case, in the sense, we took the classification of Lie superalgebras, those which are come from, those who were absolute coming from characteristic 0, we don't look at them, we look at exceptions, and for each exception we find a Nichols algebra. So it's not magic, there is a formula relating, but so we start from the literature, also for modular, for super.
Let's thank Nicolás again. So we have a coffee break now until 11:45.
So I forgot that I had to give the microphone for the questions. Should we repeat?